Good afternoon, everybody. We are going to start session 2. The chair of this session is Professor Hilda Cerdeira. And in this session, we have 2 talks. One is Satyendranath Bose, his education, teaching and research by Saifur Rahman. And second one, in fact, the third one, NASA Technologies for Space Exploration by Gautam Chattopadhyay. Okay. So please welcome Professor Hilda Cerdeira as a session chair. Oh, this. Yeah. Oh, sure. Okay, no problem. So this is your session.
You can also read from here.
Good afternoon. So we are going to start the session with Professor Saifur Rahman, who's going to speak on Satyendranath Bose, his education, teaching and research. And so please.
Put that in. Good afternoon. You had a good lunch. If you fall asleep, I would not mind. But I'll try to keep you awake with my talk. So the thing is, when I heard Dr. Parvez's comment, I changed the title of my talk. It's no longer his research. And also Dr. Yunus. He said we have to use this event, occasion, as our stepping stone for younger people in the back, stepping stone. That's why I said legacy for the future. I'll say exactly that. Legacy, আপনারা শুনেছেন, sorry, Bangla সবাই বোঝে মোটামুটি. Anyway, we heard the 3 talks this morning about his legacy, including Partha Shahan and the rest. Now look at, having seen, heard that, what can we do to bring his contributions to attention of young people who will feel motivated to great things because it has been done in Curzon Hall. That's the mission. So I hope that message gets through. So let's get the slides. Okay. Thank you. So the reason I'm using this template, when the president of IEEE speaks, he must use the IEEE template. Otherwise, not IEEE speech. So that's why it is. Just please move on. So this is, it's a good point I show this building. It's a good-looking building. It's my office. The point is not the building. Point is the URL at the bottom, srahman.org. Why I do this? All lectures I give are posted on this website. So this is where you'll see it tonight. And you can tell I'm an open source person. All the talks I have given, files are on this website. Everything I've done last 3-4 years. So no need to take pictures. Just listen to me, then ask questions. You will have the slide deck in front of you tonight. Okay, so this is an example of what you'll see. This is the screen capture from my website on the presentation tab. Go there, see the talk I gave last is here. Now, this is very important. You have seen this picture outside. Partha Shah might know, Partha Ghosh, you might know what was his lens power. -13. Really thick lens, -13. With that, he studied and did very well. So this is, and he says, idealism, however impractical, gives a meaning to our existence. I believe in that. Idealism can be very impractical, but don't stay away from idealism. This is how I try to lead my life. So this is where we are coming from. This is, very quickly, and most of you know this already, but I'm going to put it there. Hindu School in Kolkata, Presidency College Intermediate, Calcutta University. Then he went to Science College. Let's go see this. Presidency, Science College. He was teaching there as lecturer when the Dhaka University Vice Chancellor came, 1921, and recruited him to be a faculty member in Dhaka. That's how his academic teaching life began formally in this city. So this is a very important picture. I was given this picture by Dr. Professor J.C. Bose's great grandniece. J.C. Bose had no children. So his nephew was this lady, Krishna Bose's grandfather. She gave me this picture. I gave it to Kamrul to put in the museum at Dhaka University in this case. So if you look at these names, front row is, of course, Meghnath Saha, J.C. Bose, and Janan Chandra Ghosh, 3 of them. People talk about Meghnath Saha and Jagadish and our person here, S.N. Satyendra Bose. S.N. Bose was first in his MSc exam, and then Meghnath Saha was second. So Bose was recruited by Dhaka University. Meghnath Saha is a good friend, he'll go there as well. But he didn't get a job there. He went to Madras and then came to work with him later on. These 3 in the front row. Then you have, of course, second is, left to right, Snehamay Datta, Satyendra Bose, Devendra Mohan Bose, N.R. Sen, and Janendranath Mukherjee, and A.C. Nag. Why put this in blue? All the blue names are Calcutta University graduates. So back then, Calcutta University was the birthplace of very famous scientists. And still today, it's a big powerhouse. And we hope Dhaka University, as somebody said this morning, Dr. Ibrahim said, lost a lot of well-known people after 47. So we need to go back and build this back for our problem. This is the joint Einstein-Bose picture here, and you heard plenty this morning. I'm going to repeat this, but why he was recruited, worked with Einstein, and moved on with his own life going forward. So this is important. I just summarize. He was born in, well, you heard, 1894, January 1, by the way. Then he went to Dhaka University, 21 to 45, moved on to various places, came to Kolkata back in 45, 56, then Padma Bhishan in 54, and 1959 became a national professor, which held till his demise in 1974, February 4th. So that's his chronology of his life going forward. This is the Curzon Hall, famous Curzon Hall. Those of you who have not been there. It looks prettier than in reality, by the way. It's okay, but not so nice. I went that hall back in mid-60s for a school science fair. That's how I knew Curzon Hall back then, mid-60s, right? So that's Dhaka University. This is the S.N. Bose Center in Kolkata. You see his picture in the middle? So you have the center here as well. I show this for a purpose. And to see that the Bose Center here, museum, brings his writings, his equipment, his other stuff to be visible by the young generation. Why is it important? Because, as you heard already this morning, I want to see that the young students in Dhaka University, physics especially, should know how difficult it was to work. As I said, no phone, no internet, no nothing. He accomplished so much. So with all the support we get, we can do a whole lot more than we have been doing so far. It's very, very important for the young generation to know this. So this is a newspaper clipping, 29 June 15. The university opens S.N. Bose Museum. Just almost 9 years ago. So what have we done so far? So I'm challenging, like Dr. Inus did this morning, that make this as a national treasure and our history. Yes, he was born in Kolkata. He lived long time in Kolkata. But somebody said to me recently, people tell us, well, he's an Indian scientist. To me, India is a big India, not India today. Indian subcontinent. That's how I say. Dhaka University, I was a boy. Dhaka University, my place. I want to see, he did his work here. He's Bengali speaking, and he has done so much. So I'm from Bangladesh originally. So we can claim him as our son of the soil, and we should feel proud of his accomplishments. So that's important. The reminding the professor's comment that you should claim your people, don't ask for what they believe in their personal life. That's very important. So this is going forward, how IEEE President, IEEE Leadership Board, how we help to recognize major events globally. Because it's true, we have a museum here, museum in Kolkata, somebody in South Africa, how would they know? They'll never find out. IEEE operates in 190 countries. India has second highest membership after US. Bangladesh has like 5,000 IEEE members. So we can use our network as a huge infrastructure to promote big events. So you see here, we want to show, I'll show you pretty quickly how we do this job. We have what is called milestones and medals. Milestone, I'll show you an example, how we recognize big events globally from 1751 till now. So an example. These are some milestones focusing on wireless. Why I'm talking about Jagadish Chandra Bose, wireless ideas. You see here, we have millimeter wave, telegraph, telegraphy, wireless, and many things. Two things in blue, J.C. Bose and Raman effect. We have 200 some milestones, starting with Ben Franklin in 1751 in Philadelphia. So we go a long ways. IEEE is 140 years old this year. So a lot of things are happening. These are sample of milestones out of 250 some today. So we have in India 4 milestones, these 2, and Calcutta Electric Supply Corporation, CSC, it began producing commercial power in 1898. First in South Asia, milestone. 4th one is in Pune for large antenna for space exploration, Pune. 1 Pune, 3 in Kolkata. I'm trying very hard, and Dr. Kanwal knows this, to have milestone for S.N. Bose in Dhaka. A lot of visibility you'll get all over the world because S.N. Bose was the professor here at Dhaka University. That'll take some time. That's my target, to get it done. So this is milestone, some sample. These are, you know these people. So what I'm saying here, I want to see the legacy of these 2 gentlemen as example of what can we do with Shoten Bose's legacy. For example, one is this one. We have, this is data from 2012. 2 milestones. One is Jagadish Chandra Bose. Second is C.V. Raman. Were established in Kolkata in 2012. It was done. And what was done is, this one is J.C. Bose. You can read this if you want to. It is visible now outside the main auditorium, President's University today, right now. Our milestone plaques must be in a public place so that it can be seen by anybody. For Calcutta Electric Supply Corporation, CSC is outside the building near the main gate, and one in Pune. So this is one for J.C. Bose. This is for C.V. Raman, is in association for the College of Science in Kolkata. That's the building where this is stationed. This is a place where there's some equipment that J.C. Bose worked on. So this is a second milestone. I hope we collect enough information. I'll have a pitch right now for Partha Ghosh. We need 3 endorsements with the application. And if you know the person, which you do, we can ask you for an endorsement. And that goes to IEEE History Center. Use that information to decide if the milestone can be awarded for this person's work. So this is the challenge I want to take up, and with the help of Bangladesh IEEE section, we can move forward. And we have a mother of one of the section leaders sitting here who will be a good person to move this forward. Again, that's number 2. So this is set of 200 some milestones. Next is medals. Milestone plaque is visible in that building. We have 21 medals in IEEE, starting from Thomas Edison. Those are given every year, awards, like Nobel Prize, and those are done in special places. It was in Atlanta last year, in Boston last year, it'll be in Tokyo next year. That means when you have some medal for person X, that person's name is printed on the brochure and on the website every year. That name will be visible every year, almost forever. That's why, to me, medal is also very important because it gives you global visibility. Again, following Professor Inus's comments, we have to let the world know this was done here. So our students, especially young professionals, feel proud of the accomplishments and move on to do things on their own. So that's the medal picture. So these are two very important. Out of 21 medals, only 2 are outside US and Europe, only 2. One Japan, one J.C. Bose, which I did last year. This was a very brand new medal. So out of 21, only 2 are outside US and Europe. So these are the list of 21 medals. I highlighted here 2 things. Jagadish Chandra Bosu Medal, which will go given first time next year, 25. And the first one is Edison Medal, was given 1904, 120 years ago now. Just show you the depth of this medal's value. It's very important, very visible, because we have nominations, those medals, nominations. That means people will look for somebody who is very well known in wireless communications today. So then that community gets energized. They'll know who is J.C. Bose. Why is it important? Typically, a person who gets the medal is very well known, professor or industry scientist, typically. But nominations come from many places. So for this case, this year, nomination has been done. It'll be approved by the board next week, 2 weeks from now, and then it will be given in Tokyo at our medal ceremony. That's how it works. So this is another set of 7. You can get some names that look familiar to you. You'll see many physicists here, physicist names. Electrical engineering and physics have a lot of interaction, and we want to make sure that stays that way. So physics, to me, is the closest to engineering, and vice versa. And physics is something I liked from young childhood. I did very well in East Pakistan, got highest mark in physics in the higher secondary exam in East Pakistan at the time. So I have kept that. One example, I finished my higher secondary in some years ago. I was going to BOET with a 6-month gap. The results came out in June year X. The BOET starts January year next year. So I went to Notre Dame College. Some of you may know Notre Dame College here. The physics prof said, you're sitting for 6 months, why don't you become a demonstrator in physics lab and in this college? So I'm teaching physics since I was 18 years old. So this is how my connection. Anyways, what happened at that time, I was waiting for getting admission or classes start at BOET, January next year. So I went to see the Dhaka University dean for some reason. He said, you're sitting doing nothing, just start the class here. So if you may like it in physics, you may not go back. Just go to in physics. So I did not do that for some reason. So this is how the connection is. So you see these names doesn't matter anymore. Many physicists here. This is the medal for Jagadish Chandra Bose medal. This is the medal. This is a bronze medal, pretty good size. It will be given out for the first time in April 25 in Tokyo. So now, how do we know the medal is useful? The very important picture here. Medals need money. We need $1 million plus to do a medal because income has to be enough to pay the expense and all this stuff for the medal. So question is, who will give $1 million? I will never use this own money for medals because it has to be done by the person, company, or somebody who wants to recognize this, J.C. Bose in this case. There's a professor, retired UCLA professor, Dr. Monilal Bhomik. He's the first PhD from IITs, first ever PhD, IIT PhD. He retired. He agreed to fund this medal endowment, which he did. So you can see here, this came out in the January 7 issue of Times of India. It says here, it's saying, Indian American Scientist Funds Award in honor of J.C. Bose. I felt very proud, Times of India front page coverage for medal announcement. I was president then, said that looks good. When my name is mentioned there, if you can read the fine prints. The point is, it takes some time to get things going. So anyway, we moved on. So this is the ceremony. We recruited a US congressman with Indian origin, Krishnamurthy, to let us use the US Congress building auditorium to announce this medal. January 12, I think, this 2024. So there you see, on my right is Monilal Bhaumik. On his right is the US Indian Embassy Charge d'Affaires and other people, which is interesting. And in that case, this is important on the right. The Krishna Bose, she is the great-grand-niece of Jagadish Chandra Bose. She gave me that framed picture from her family collection. I took that and gave it to Kamal Hassan for Dhaka University Bose Museum. On the left-hand side, very important, I invited the Bangladesh ambassador in Washington to come and talk. Why? Well, even though J.C. Bose is an Indian scientist, to me, India means the big India, not just today's India. And he was born in Munshiganj, a 3 hours drive from here. So I said, we should claim Jagadish Chandra Bose as a Bangladeshi-born scientist, because he grew up in this part of the country. So we want to make sure we're inclusive, to Professor's comment, inclusive. Do not let his religion be the yardstick. So the ambassador came and spoke, and Moni Bhaumik is there. So this is another example of Krishna Bose talking to the audience about how and what she knows of Jagadish Chandra Bose. Point is, don't be shy to promote your history, legacy, and use that legacy to claim fame and build on it. So I was very sad to hear from Dr. Pervez said about Abdul Salam's situation in Pakistan now. So this is how I would like to see we think, be inclusive, not keeping people out for other reasons that we may not want or know. So this is my final message. Let's work together to promote the impact of Professor Satyendra Bose's work globally. IEEE milestone, IEEE medal, IEEE section events can all bring it in. In fact, I would like to see Dhaka-based IEEE section do an event this year, 125th year, of Professor Satyendra Bose's contributions, and bring young people to see what can be done, and maybe do an essay competition and give some award, the best essay about what Satyendra Bose did, how he did it, and how that research is relevant even today to do that. So that's it from me for now. I've given you my email address. If you want to write to me, please do. I also give you my website where this slide deck will be on tonight. With that, thank you for your attention. I appreciate your willingness to hear me out. Thank you very much.
Hello, any talks, any questions? Please, who has the, yeah.
So I met Monilal Bhaumik last year when I was visiting the Perimeter Institute in Canada, and they were doing a special event on S.N. Bose. So he was S.N. Bose's student. Yeah, direct student. And Monilal Bhaumik said that, both his PhD and postdoc positions that he got, either the PhD or the postdoc, SN Bose played an active role. So I think that, he's a billionaire, right? I mean, he made billions doing laser. So even with this, with SN Bose medal, we can ask Monilal if he wants to fund this.
Thank you.
I should add something to since him bring it up. Monilal Bhome gave us $1 million for the J.C. Bose medal. When Kamrul was arranging this meeting, he was looking for sponsorship. So I wrote to Monilal Bhome, can you put some money for this conference? He said, well, let me think about it. So it's just thinking, maybe next year he'll do something different.
Another question?
Right here, Mike,
Sure.
this lady.
This lady here.
Thank you very much for your most forward-looking legacy. I just want to inform that Buet has a Shotten Bose Science Club. So there are many students associated with that science club. They are on the Facebook. So whenever I post something, I mark it to this Shotten Bose Science Club. So anything you'd like to do through IEEE, please just remember about that science club also. Along with our students of Dhaka University also, for the legacy in future.
Any other question? Yeah, here, there. No more questions? I have one. Yeah, I have a question. The point is, I see that you've been focusing in engineering. My question is, what are they doing here in Bangladesh to control, let's put it this way, I don't know how to call it otherwise, to control the advance of artificial intelligence, because it can be very harmful. So
I don't know Bangladesh's situation in AI today, but I have heard Jeffrey Hinton, this is physics Nobel laureate this year. If you follow physics and chemistry, the 2 in physics, 3 in chemistry. Out of 5, 4 worked on AI, not chemistry equation, AI. It's a big deal now. So Jeff Hinton was asked this question. It can be very dangerous. If you don't have any guardrails, the AI machine will be more than your intelligence can handle. They'll tell you what to do. So his answer was, we must require the developers to have some kill switch. If the machine is so smart, it can kill me, I'm going to kill him before it kills me. So this is the American approach to do this. EU and China both have guardrails now. I was at the AI conference in Zurich 3 days ago. They're saying because of the EU restrictions, they're not so innovative anymore. There's other risk. So innovation is what you want, but you should not be controlled by what you have innovated. One quick thing for the students in the back, I gave a talk last year, this time in Shanghai, the World AI Congress. Students asked me after my talk, how should I use AI in my work? I said, use AI as an assistant, not as a teacher. We use the word co-pilot. So let AI help you to do where you want to go. You decide where you want to go. And it gives you help, but not let it tell you where you should go. You should not give up your brain power to just sit back and let system tell you what you should do. That's my big picture issue.
I just want to thank you. I think you have a very optimistic view of the problem, because I've seen these things in my country. I come from Brazil, and where essentially AI is used by companies, big and small, and And what happens is people are losing their jobs.
That's a different story.
So that's I mean, not to enter into scientific details, you see, because I do understand that in many cases when you use machine learning or things like that, it can help you to get to do research. But as you say, in that case, it can be controlled.
One final thing. 3 weeks ago, U.S. Eastern Shore had a dog worker strike. You want more money, but number one was cannot use AI for your operations. So we become irrelevant. Cannot use AI for your operations. Cannot make your operations smarter with AI. So there's settled out of other reasons, but that's the way people are thinking. I lose my job because AI will do the job which I used to do. But that's a bigger issue. We cannot have time to go into any depth here. Thank you very much. I appreciate it. Bye-bye.
Thank you very much. So let's go to next speaker. The second.
The next speaker is absent.
The second. We should go to this one? Okay. Is he coming back? No, the second. Is he coming back?
Coming back.
Oh, okay. We see what we do later if we jump. Okay. So then we go to the third talk, which is by Gautam Chattopadhyay from NASA Technologies for Space Exploration. And wait a minute, I'm going to find your talk. So I'll tell you the title in a few minutes. It could be in alphabetic? No, here. Oh, that was the title. I thought that was the name of. I thought that was the name of the company. Okay, he's going to talk about NASA Technologies for Space Exploration. Thank you.
Thank you very much. All right.
You don't need to. You just check this one.
Yeah.
This one.
This way. No, my talk is not uploaded.
Oh, not uploaded. Right. Okay.
Just let me upload it. Yeah. Yeah, it's coming up. Yeah. Let me just, where is the cursor? I cannot see the cursor. Let me see.
It starts
Yeah, if I can reach there. Where is the cursor? Oh, found it. Slideshow.
from the beginning.
All right. Okay, good afternoon, everyone. I'm really honored to be invited here and give this talk. I grew up about 300 kilometers from here, near Kolkata, but never got the opportunity to come to Bangladesh. This is my first trip to Bangladesh. It's like the famous poem by Rabindranath Tagore, দেখা হয় নাই চক্ষু মেলিয়া ঘর হতে শুধু দুই পা ফেলিয়া একটি ধানের শীষের ওপর একটি শিশির বিন্দু. So that's what I feel about myself. So I am not a physicist by training. I am an electrical engineer, so what am I doing here? The thing is that if, as a kid, if you have grown up in this part of the world, I don't think there is anyone who has not dreamt about, thought about S.N. Bose, J.C. Bose, Meghnad Saha, Prashant Chandra Mahalanobis, and all those people. So we had the richness of scientific exploration in our part of the world, and that inspired all of us. And maybe in that role, I am here. So I'm going to talk to you a little bit about some of the technologies that we do at NASA. Of course, I won't be able to talk all the technologies. But whatever we do at NASA actually is the basics of that is science. You might be knowing about all the different cool technologies we do. However, everything is for science. We are trying to answer science questions, big science questions. And that's how we go about it. So what is the big science question we are trying to answer? And to answer that science question, what kind of measurements we'll have to do? To do that measurement, what kind of instruments we'll have to build? To build that instrument, what kind of technology gaps that exist? And then we develop new technologies. And that's how innovations come. So that's what I'm going to talk to you about. So let's start. Okay, which is not moving forward. Let's see. I'm pressing those arrows, but it's not going anywhere. Okay, it happened. Good. So a little bit about NASA JPL. You know that NASA has a lot of centers all across the United States. Our headquarters is in Washington, D.C. However, I come from JPL, that is on the West Coast. JPL actually is the largest NASA lab. We have more than about 6,000 people. And in a way, NASA started from JPL. JPL is older than NASA. So few professors at Caltech were doing some propulsion experiments, and then the JPL was born. So a little bit more about JPL. We have, as I said, about 5,500 people. Our yearly budget is about $2 billion. And we have been very busy. If you look at these, some of these programs, some of the missions that we are flying right now, and some of them are being planned, and many of them are actually built and developed and conceptualized in our lab at JPL. We are the largest robotics lab. We do not do manned missions. We do technologies. So one of the things we do is we dare mighty things. This is actually the word from our immediate past director of JPL, Charles Ilachi, that we dare mighty things. Let's see what we have been doing. We are studying our own planet from air and space, trying to understand what is happening due to climate change is very important for the young generation, for all of us. We are looking for life beyond Earth. I'll explain a little bit more about it. We are creating robots where no human can go and do things. And also we are trying to explore our own solar system. And we have been doing that. Look at this Voyager. Many of you know Voyager, interstellar space, which launched in 1977. And it is still going. That is the farthest any man-made object has ever gone, Voyager 1. And in terms of distance, it is about 22 light hours away. We know about light years, but this is 22 light hours. That is about 24 billion kilometers. That is huge. If you think about it, the distance between Sun and us is about 150 million kilometers. That tells you how far Voyager is gone, and still it's communicating. We are getting data. Of course, you cannot download in a video like YouTube video you do. It's a very low data rate, but still, it is sending data saying, yes, I'm alive. Mostly health data and a little bit of scientific data. It's going on. So to start with what we do and what kind of instruments we are building, let's start with the Big Bang Theory. This is not the Big Bang Theory that you watch on TV. This is the real Big Bang, that we believe that the universe started with a Big Bang. Made all of your physicists, I won't have to tell you about Big Bang. But one interesting story about Big Bang is that first light, we all know, that came out is about 380,000 years after Big Bang, cosmic microwave background radiation. And is very, for the students, is a good story that two gentlemen, Penzias and Wilson, Bob Wilson and Arno Penzias, they are doing some experiment, millimeter wave experiments. If you are electrical engineering or physics student, you know that millimeter wave nowadays is a big thing for communication. Everyone says, oh, that is a big thing because your 5G, 6G is millimeter wave. These people were doing their millimeter wave communication experiments in 1960s. And when they were doing that experiment, they were finding that there's some extra bit of noise in their measurement that they could not explain. And they found that wherever they are looking, they change their antenna, these are cooled detectors, very sensitive detectors. They're still getting a little bit of extra noise. that they could not explain. Many of you do your experiments in the lab, in a physics lab perhaps, and sometimes when you cannot explain something, what do? You think it must be experimental error. So you just make your error bar slightly larger and then say, I'm done. They were not like me or you. So they started scratching their head, and then they realized that they were looking at the first light of the universe. And for that work, they went on to win the Nobel Prize in 1974. So next time you are doing some experiment in your lab and you cannot explain something, don't think that is experimental error. You might win the Nobel Prize, you never know. So what we are doing, of course, we are trying to answer big science question, as I said. How does the universe work? How did we get here? And one of the biggest science question we are trying to answer is, are we alone in this universe? Is there life outside our planet Earth? Just to be clear, I want to make one point extremely clear, that whatever you see on YouTube, whatever we read on the internet about aliens, we have not found any life, any form of life, anywhere outside our planet Earth, not even a single cell. So if some of your friends say that they have seen alien, please ask them to talk to us so that we'll stop spending billions of dollars answering that question. So, but the question is there possibility of life outside our planet Earth? Answer is yes. Let's do a thought experiment. When you look in the sky, what we see is the millions of stars. That is our Milky Way galaxy, Akash Ganga, we call it. In that galaxy, we have about order of magnitude 100 billion stars. And in our universe, we have about 100 billion galaxies. So order of magnitude, you are talking about 10 to the power 22, 10 to the power 23 stars in this universe. And we are finding the majority of those stars have planets around them. And not one, multiple of them. And many of them are in the what you call habitable zone. Habitable zone is where the conditions are such that life can exist. So what is the probability that we find one such planet where conditions are such that life can exist? That's a non-zero probability, and we are trying to find those kind of planets. And when we are looking for life, we are actually looking for our kind of life that we know, hydrocarbon-based life. You might say that could be other kind of life. Yes, but how do you search for it? What do you search for it? That's why we search for our kind of life. There's a beautiful song by Tagore. I always give that example. Many of you know, as a Bengali, who doesn't know Tagore songs? In that, one of the line he says, Janar majhe ajanare korechi sandhan, which means when we are searching for unknown, we search with what we know. And that's why we are actually searching of our kind of life, hydrocarbon-based life. We have actually found about 5,000 plus exoplanets so far. The reason for that is we have not really searched far, only in our own galaxies. And many of them, you can see they're gaseous giants like Jupiter, which cannot have life, but we have rocky planets. We have planets where water can exist. The temperature is such that life can exist. Water can be found at room temperature. Those are the kind of planets we are looking for. The nearest planet that we found of that kind is about 4 light years away. It will take 40 million years to go there with our current day technology, which means we won't be able to go in our lifetime, for sure. So we'll have to develop technologies to find out, is there any atmosphere? Is there any oxygen? You know, the building blocks for life are only few elements. We call it chonops: carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. These are the things that we need of our kind of life. So we are actually looking for in the atmosphere, is it available? Very high resolution spectroscopy that we are doing, trying to find out about those. Okay, we won't be able to go to those kind of planets in our lifetime. How about possibility of life in our own solar system? This is Enceladus. a moon of Saturn. What you are looking at is water gushing out. This is actually water gushing out. And it was actually detected by one of the instruments called Herschel Hi-Fi instrument. And I was very fortunate to be I developed the part of the instrument of Hi-Fi. And that detected that water is gushing out. This is a very cold planetary body where there is all ice. If water is gushing out, that means it has to have a source of energy. If there is a source of energy, if there is water, is there life? We don't know. So NASA is actually planning a mission to go to Enceladus and trying to find out what else is coming out. There is another planetary body, very interesting, recently you must have heard, is Europa. There could be life, possibility of life in Europa. Why? What you see here is Europa, we know, scientists, we know that it is actually, again, very cold planetary body and very thick ice shell on the top, but there is a liquid water ocean underneath the ice shell. The thickness of this ice shell is about 15 kilometers to 100 kilometers. Since it's liquid water, there has to be a mantle that is a source of power. So is there life in this water of Europa? We don't know. So NASA actually launched a mission for Europa Clipper mission that was launched last month. It takes 7 years to go there. So for the students, suppose NASA had come to you and said, okay, we are going to go to Europa and trying to find out if there is any life in the water ocean of Europa. What kind of instrument you are going to build? So obvious answer is that we are going to send a drill a hole, lower a bucket, and see if there is any fish. All bongs will like fish. The problem is, as I said, it takes 7 years to go to Europa. And the total amount of power available for this kind of missions is about 400 watts, 4 light bulbs. So what kind of drill you can send there with 400 watts to drill 15 to 100 kilometers through ice? It's not going to happen. Which means you'll have to think outside the box. So we have built a lot of instruments, very high spectral resolution, detectors. So what happens is all the materials from this ocean, they seep all the way to the top surface because there are cracks. But when you go to the top, it freezes. However, Europa is very close to Jupiter, and Jupiter is very high magnetic field, very extremely high radiation environment. So what the radiation does is sputters all the material in the atmosphere, and we are actually sending a GPR, ground penetrating radar. We have sent some high resolution spectrometer to see if there any organic materials, is there any life kind of material is out there or not. So organics are not necessarily life, but is the precursor to life. So that's what we are looking for. And also, of course, we keep going back to Mars because Mars, in its early history, resembles so much like our own planet. And of course, it's the closest neighbor. It takes only 7 months to go to Mars. So we have been building all these rovers to go to Mars. So we started with Pathfinder in 1996, very small rover, you can see. Then we twin rover Spirit and Opportunity, then Curiosity, and latest one in 2020, we sent Perseverance rover. This is one of the most expensive self-driving car you can think of. It has a lot of different instruments to do all these experiments. This is just before this instrument was packed up for launch in our lab here. And going to Mars and landing on Mars is not easy. It's extremely challenging. You can do that launch once in 2 years only, because that's when the distance between Earth and Mars is such that it is the lowest, so that we can actually reach Mars with our current technology. So cruising speed, you can see here what happens. This is the orbit of Mars, the orange, and blue is the orbit of planet Earth around Sun, and this is the orbit of our spacecraft. The cruising speed of this spacecraft is about 70,000 kilometers per hour. And we arrive at the apex point here just before Mars comes, so that Mars comes from behind and catches up. Because if timing is little bit off, we are going to miss each other completely. And then we'll have to slow down to about 10 to 15,000 kilometers per hour. And Mars atmosphere, the density of Mars atmosphere is only 1% of planet Earth, which means we do not have enough friction to slow us down. So we have to enter at very specific angle, about 11 degrees, and then we slow down with a lot of thrusters. We have a parachute that gets deployed, and a lot of things has to happen, has to go right. So landing on Mars is extremely challenging. That's why not many countries have been successful in landing on Mars. So if I show some of these pictures and tell you maybe this is one of the road in Dhaka during monsoon season, you might say, yes, it looks like that. Or perhaps in Kolkata, perhaps. But no, these are all from Mars. And look at them carefully. You get this kind of terrain only when there is flowing water. When you go to Mars today, we don't see flowing water. Mars hardly has any water. The question is, what happened? Where did that water go? Can it happen to our own planet? These are very important questions for us to answer. And that's what you're trying to understand. And that's why you're trying to build instrument to go there and answer those questions. So I'll talk about technology as well. I'm setting it up for you. Another, as I said, to have our kind of life, we need water. However, when our planet Earth was formed, there's no water. How many of you know that? And scientists believe that comets brought water to Earth. Comets actually carry a huge amount of water. Of course, not the entire water of this world. They brought the seeds of water. But that is still a scientific theory. How do you prove? If you ask me that how do you go about proving it, that comets brought water to Earth? It turns out the water that we drink, that water that we are all drinking right now, is H216O. Oxygen has different isotopes. The most stable water is H216O, most abundant water, but there are other kinds of water. H217O, H218O, HDO, one hydrogen, one deuterium, and oxygen also creates water. And heavy water that in nuclear power plants we use, D2O. If you take the ratio of abundance of different kinds of water that is available, it turns out our planet Earth's water, this ratio of abundance is very similar to one kind of comet called Jupiter family comet. If the abundance is same, D over H ratio is the same, then the source is the same. Unfortunately, we have made only about 10 such measurements on comets. And many of the measurements are showing perfectly good alignment. Most recent one that we did in Rosetta, we are finding that this ratio is completely off. So that the question has not been settled yet. So I now will talk a little bit about technology. So I decided that, okay, can we do something about it? Can we try to answer this question for once and all? So I wrote a proposal to NASA saying, and the name of my instrument was Water Hunting Advanced Terahertz Spectrometer on Ultra Small Platform. What's up? Because we wanted to answer the question, what's up with water? Maybe because of the acronym, my proposal was selected, so we are trying to build an instrument, and this small instrument in a shoebox-sized satellite that miniaturize everything, put in small satellite, get a ride. When there is some other mission going on, they can throw us out, and we have our own propulsion, go to comets, as many comets as possible. We can make multiple copies of this, and then do the measurement and answer this question for once and all. So how do you go about building such an instrument? Since morning we are talking about we'll have to have open minds and knowledge, pursuit of knowledge, and pursuit of innovation, new ideas. These are needed. How does innovation happen? You do not wake up in the morning one day and say, let's innovate something today. It doesn't happen that way. We face problems, we face challenges, and then we try to come up with a solution, and that's when innovation happens. Look at this. As an engineer, as a scientist, we always start with a block diagram. So this is the block diagram of an instrument that we are building. Actually, we built already. So we start with an antenna, very small antenna, very low profile antenna. This is the frequency band we are talking about. Is, as I said, this is a very high spectral resolution spectrometer. We are trying to look at these lines. So HDO is 509 gigahertz. Just in comparison, your cell phone, the 5G, 4G, LTE works at about 4 gigahertz. This is 500 gigahertz. So 2 order of magnitude higher in frequency, very challenging. Then H2 18O is 548 gigahertz, 17O 552, and most common water 557 gigahertz. We need a very low profile antenna. We need a synthesizer. We need back-end spectrometer, and we also need to calibrate our instrument. These are the need, and let's look at all these different challenges. So if you look at an antenna, if you have seen reflector antennas on your roof sometimes, they're large. You will see there is something hanging out in further off, that's called subreflector, so it takes a lot of volume. You cannot fit this kind of antenna in a very small shoebox-sized satellite. So you'll have to come up with a new kind of antenna technology. Then you'll have to make a switch. It's called Dhaka switch for calibration. If you're trying to measure something, first thing you'll have to measure a standard that you know about, and then compare your measurement with that standard so that you know what you are measuring is correct. So one of the ways it's done is with a switch called Dhaka switch. You look at a standard load, a black body load, and then you look back at the signal that you are getting. Unfortunately, at this frequency, no such switch is available. You cannot buy, you cannot procure any such switch. That means you'll have to come up with an idea to build some switch. If you buy a synthesizer you need, many of you know a synthesizer in your lab. If you look at that, it's very heavy, weighs about 10 kilograms, and it also draws about 10 to 15 watts of power. The instrument that we are trying to build will be weighing less than 2 kilograms and needs only 5 watts of power. So you cannot use what is available out there. So you'll have to come up with a solution yourself. And back-end spectrometer is a spectrum analyzer. Again, a spectrum analyzer in your lab is about 10 kilograms in mass. So you cannot use them. So we actually built some of these. This is an antenna that we built, very low profile antenna. You can see here it weighs really very less. And then we also built another antenna, is a lens antenna. It is very thin, only about 5 centimeter in thickness at this frequency. And then this weighs hardly anything. This antenna weighs less than 500 grams total. That's how we can make a 2 kilogram instrument. And then when you are building such things, you'll have to test them as well. As we have been saying all this time, that testing and proving what you are doing is very, very important scientifically. And then we actually we measure the efficiency of this antenna. We have built a 200 millimeter, 20 centimeter antenna. And as I'm talking to you about the switch, you'll have to make a switch. It is not available. Low loss switches are not available in the market. So we came up with a MEMS-based solution. What you see here, let me put on my teacher's hat. Many of you know about waveguides. You must have studied waveguides and cutoff frequency of waveguides in your physics class. If you look at a rectangular waveguide, its cutoff frequency, it depends on the A dimension of the waveguide, because C over 2A is your cutoff frequency, is a high frequency, high pass filter. So if you look at a waveguide, and if you change the A dimension of the waveguide, it can turn it off and on. So in a MEMS structure, we actually built it, and this is at 500 gigahertz. So these are two waveguides, these orange rectangular waveguides. The dimension of them are 500 micron by 250 micron. The thickness of your hair is about 150 micron. And this is metal. So we are cutting metal with a piece of hair in this case. So extremely challenging to do that. So what you are seeing is that this is a video showing that if this arm, in the MEMS arm, is going in and out of the waveguide, that actually makes one of the thing under cutoff, the other one open. That's how we can make a switch. And it's an extremely low loss switch. That's how we built it. And it's working. It's under microscope because you cannot see such a small waveguide. So it's a metallic waveguide with that kind of dimension. So it's working great. So we also made another kind of switch where you can move a metal U-shaped structure from one end to the other, but two pieces of metal cannot rub against each other. So you'll have to keep a gap, and so that there is no leakage of energies, we created something called EBG, electromagnetic band gap structures, so that there is no leakage. So anyway, it works very well. I'll show you a video. This is the actual waveguide. You can see here again, these are metallic waveguides. And the dimension of this one, this is again about 500 micron by 250 micron. Extremely small. And then so you can make a switch like this, and you can make the other using, this is called SoC. SoCs are system on a chip. The technology that is there in your cell phone, that we are using to build instruments for outer space. You cannot send your iPhone to space. It is not going to last for more than a few seconds. So you'll have to, when you are building this kind of instruments, you'll have to make sure they are not destroyed by these cosmic rays that you see in the space. So we actually are building our own chips. This is a 65 nanometer node chip that we have built. You can see here the phase noise is important for this kind of chips. And the total amount of power this synthesizer draws at 90 gigahertz is less than half a watt. If you are, as I said, if you are buying something outside, it will draw about 10 watts. This is half a watt. And that's how we are able to make things small and very compact. And the synthesizer, the spectrum analyzer, again, it draws about 1.6 watt. And then we put everything together. This is how it looks like, the instrument. There are two versions of the instrument. One is with the reflector antenna. The other one is with the lens antenna that I told you about. Now you can see the size. Current generation, previous generation of instruments, of this kind of instruments, was kind of this desk. Now we have made it really small. And to test that, we actually flew it on a balloon. And you can see here that we have put our own alien, Bob the alien, on our balloon gondola. There is a reason for that, I'll tell you, because we flew this balloon from a town called Fort Sumner, New Mexico, which is very close to another town called Roswell. Roswell, New Mexico is a very interesting town. People believe there that the first alien landed. So if you go to that town, you'll find everything is all alien-based. So our balloon was supposed to actually land after it flew very close to Roswell. So we actually put our own alien so that they discover the second one in that part. So again, here is some just preparation for whenever you are doing experiments. You will have to make sure that you put everything together, test everything together, and you are actually do some measurement to make sure that whatever you are measuring is right. Otherwise, you are going to get a wrong answer. So it's very important to do that. So this is the launch of the balloon. As you can see, this is being launched from one of the town there. So we release this balloon. And this is very high-tech because we are holding our gondola in hand here. And then we release. So this balloon climbs all the way, climbed up all the way about 120,000 feet and did the measurement from there. And then it lands after about a couple of hours, it lands. So there is a parachute so that when the balloon, the gondola lands, it doesn't crash land. Unfortunately, the parachute didn't really work very well. So all the instrument landed on the ground at 40 miles per hour. So that is kind of a big car crash. So, but the best part of it is that when we recovered this, and we found that every single part of the instrument still working as is, except for this lens came off. So, which means that when you build something like this, you'll have to make sure that it also survives this kind of, crash. And then we actually did some measurement. This is ozone that we see about 120,000 feet. And this is our measured data. And this is the model of the ozone line at that. You can see it's very close to what the measurement is. So right now, we are actually ready with our instrument to get a ride. We built multiple copies of this. So when we get a ride, they will throw us out, and we are going to go to multiple comets. And in future, hopefully, we'll do the measurement and come back and tell you whether comets really brought water to Earth or not. So I'm almost done. I'll just end with one thing, because this is very important, particularly for the students. Many of you know the story of Ingenuity. Ingenuity is a helicopter that he flew on Mars. And you might say, why is a big thing to fly a helicopter on Mars? And why are you going to fly a helicopter on Mars? The reason we need to fly a helicopter or a drone on Mars is because when you send a rover, the rover cannot go everywhere. It takes about 11 minutes for signal from at the speed of light to reach from here to Mars. So we cannot do a drive, backseat driving from here, and the limited mobility of that rover. So we thought that if we have a helicopter that can, or a drone that can take off, go around, do some reconnaissance, send the data back to the rover, and then the rover can go and do more experiments. Problem is, as I said, on Mars, the density of the atmosphere is 1% of planet Earth. So there is not enough lift. When a helicopter flies on planet Earth, the rotor, it rotates at about 400 RPM, 400 revolution per minute. For the same, rotor has to rotate at 3000 RPM on Mars to get the lift. So we had to really do a lot of innovative work to make a helicopter ready, and it flew. So when we built it, this was for demonstration only, take demo. We planned to do it only 3 flights. And then we'll say, okay, it works. Then we tried to, but it was not breaking. After 3 flights, it was still working. NASA extended the life. And then we flew 72 times. And it was still not breaking. We were trying to fly it faster. We were trying to fly it higher. We were trying to ask how far it can go. But this small little instrument was flying all the time and doing really great in collecting data. However, on January 18, 2024, earlier this year, while landing, it just clipped its wing, and it is now resting on Mars. So, but we got great data. On top of that, why it is important for planet Earth as well. Sometimes we have, high altitude, there is some rescue operation that we do, like in Himalayas, people get stuck. We cannot fly a helicopter there, because helicopter cannot fly in that light atmosphere. However, we actually have this technology now that can fly to those places, drop some communication equipment, drop some of these very necessity stuff. So we are using this kind of helicopters for future rescue operations. And with that, I'll end. Thank you very much.
Thank you very much. It was a very, very good talk. So, any questions? Yes.
For detecting water, how would you compare the sensitivity of your equipment with that of the James Webb Space Telescope, which can look at exoplanets and determine that there's water out there? You were just looking at comets which are going around the sun.
Yes, it's a very good question. The difference is that James Webb is at L2, Lagrange 2 point, and looking at farthest of places. We are going close to the comet. We will be about maybe 1 kilometer or 2 kilometers orbit of the comet. So our sensitivities, of course, these are all room temperature detectors. James Webb Space Telescope detectors are all cryogenically cooled. So they are much more sensitive than what we have. But we do not need as much sensitivity because we'll be very close to those comets. And we'll be able to still measure with parts per trillion kind of accuracy.
In terms of the spectroscopy of the water,
Yes.
how many different kinds can you detect?
We actually can detect all these, as I said, different water has different frequencies, signatures, HDO, H218O, H217O. On top of that, there are other kinds of water, ortho, para, different kinds. They all have different frequencies associated with them because they have different spectroscopic lines. So we can, for this instrument, we are depending on the bandwidth, how much bandwidth your instrument can have, we can see from all the way from 500 gigahertz to about 1.2 terahertz. And most of these strong water lines, has all the different kinds, are in that frequency band.
Any more questions? Do you see any?
I don't see any.
No? Eyes?
Oh, thank you. Thank you very much.
Well, if not, if there are no others, let's thank the speaker again.
Thank you.
And, has Professor Abul Azhar come back? No? Because, I mean, he So now we go for the tea break, and we'll have to be back in about, I don't know, in about 20 minutes. Okay.